Okay, well, it is 4 o'clock my time, 7 o'clock on the East Coast, so we're going to get started. Welcome to Key Curriculum Press's webinar on integration with Sketchpad. My name is Andres Marty. I am an editor at Key Curriculum Press, and I will just be moderating the presentation. The presenter today will be Scott Steckety, who works for KCP Technologies and has worked with Sketchpad and developing educational activities with Sketchpad for a good part of the last 2 decades. We also have with us Karen Greenhouse and Elizabeth DeCarly, who will both be answering questions at any point during the presentation. If you have questions, you can type them into the question panel in the GoToWebinar control panel, and either Karen or Elizabeth or myself will get back to you. And you should be able to hear my voice, and if you have any problems, just let us know. So at any point during the presentation, type in a question if you need some assistance. And at this point, I'm going to hand it over to Scott. Scott, I can see your screen, but at this point, I can't hear your voice.
Okay, so you do see the screen, people.
And I hear your voice now. So without further ado, Scott, take it away.
Okay. I'm glad so many people are here tonight. It's terrific to see the interest in this topic. And let me just dig right in. A quick summary of the agenda is this. The theme tonight on integration, we're going to be concentrating on accumulating values from beginning to end, and then we're going to explore the finding of accumulating value that are enabled by the fundamental theorem. So we're going to explore the fundamental theorem of calculus. And finally, we'll finish up by looking at some examples of accumulating value, of accumulating volume of solids of rotation. So that's our agenda today. Let me say by word of introduction that I was really struck some time ago when I realized that Sketchpad, which we had developed originally as a program for doing geometry, was a really powerful way to look at calculus. And the thing that struck me, there were 2 items really. One was that calculus in many ways is the mathematics of change, and a dynamic program that emphasizes change makes a lot of sense. And the other is that visual representations, pictures, tend to be more important in calculus than just about any other mathematical area except for geometry. And that combination of the visual images and the ability to change things dynamically really makes Sketchpad a very powerful tool in calculus. I hope tonight's presentation will help to communicate that. All right, so we're going to begin with the most basic way of accumulating the value of a function. And the function we're going to look at is the speed of a car as it starts from rest. So here's our car starting at 0 feet per second. And if we drive the car, its speed goes up, 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 and levels off right around 60 feet per second. And it just continues going along at 60 feet per second. Our job is to figure out how far that car goes. Well, if you accumulate speed over a period of time, the result is a distance. And that's easiest to see when the speed is constant. So the green and white bars here divide this period of motion of the car into 3 parts. And if we look at the third part, where the motion of the car is constant, it's going here at 60 feet per second from 70 to 100 for 30 seconds. So 60 feet per second times 30 seconds means it's gone 1,800 feet. And that's pretty simple to do because the speed is constant. We could figure that out by counting up these grid cells. And the number of grid cells here, I'm not going to count them all out, but the number of grid cells here is 72. 72 grid cells, and the grid cells are 5 seconds along the x-axis and 5 feet per second along the y-axis. So each cell represents 25 feet. So multiplying that by 70, each cell represents 25 feet. There's my 2. So multiplying that by the 18 cells that we have here, by the 72 cells we have here gives us a result of 1,800 feet for this green area. The white area we can figure out similarly if we count up the grid cells. We're going to have to adjust a little bit for some pieces that are missing here, but each cell is worth 25, so maybe we're missing, something less than 10 on this one. This might bring it up to maybe 15. Maybe. We might be missing as much as 15, probably closer to 10 feet. So we can pretty easily come up with an estimate for this. It's not terribly accurate, but we got an estimate. Now we come to this section, and it's really a problem. We can count up the cells and multiply by 25, but we've got a little piece here that's extra and a little piece here that's missing, and then almost half a cell here is extra, and this is less than half a cell. And we're going to have to do a heck of a lot of estimating here, and our result is not likely to be very accurate. Well, we can make this result more accurate if we change the square size from 5 to, let's say, 2. So now each square is 2 seconds by 2 feet per second. So each square represents 4 feet. And we'll get the same result here that we did before. We can maybe do a little bit better job of guessing which of these are more than half and less than half. And here we could even take a rule and say if it's more than half covered, we'll count it. If it's less than half covered, we won't. And that may work well enough with the greater accuracy we have with the smaller cells to get us a decent result. We can get an even better result if we make the grid size even smaller, down to 1 second by 1 foot per second. And that will give us a more accurate result. In fact, if we went down to a half, we'd get an even more accurate result. But I think we're going to have some very tired and frustrated students by the time they count every one of these squares along the boundary here. And we'll make it a little easier for them by making it a hairline instead of a thick line so they can be a little more accurate. But it's a very tiresome process. So hopefully by now, or before now, we've convinced students that we need a faster way to do this, a more convenient way of essentially counting up the grid cells. And we're going to do that with some rectangles. And here's the basic idea. We're going to create some rectangles that will determine in one way or another, and I'll mention several different ways we can do them in a moment, in one way or another that will count up grid cells. And these are set up so if they count based on the left edge of the rectangle. So we get a certain number of grid cells here, and we have a nice fraction there, but since we can measure the actual area within this rectangle, we can actually get quite an accurate result for this rectangle. Now we've left some pieces out here. We're going to have some extra pieces over here. Will they balance out? Maybe they will, maybe they won't. But at least we don't have to count every single cell. And in fact, we can do the same thing that we did on the previous page of making our cells smaller and smaller. So we can take n, which is the number of rectangles we're using here, and increase it. So instead of n equals 6, let's go to 12. Let's say I've selected n. I'm going to press plus on my keyboard. So now we've got rectangles that are half the size. And we've actually got a sum here pre-calculated for us. And I'll show you in a moment how we calculate those ourselves. But if you watch that number, when we were at 6, it was 38.5. At 12, it's 38.875. It's approaching 39. Let's make it bigger and bigger. Are we ever going to hit 39 totally? Well, since we can make the rectangles as narrow as we want, we can get more and more and more accurate. And it looks like we might actually hit, we can get there? You can hardly see the, I have 262 rectangles already, which is far more than the screen can actually show effectively. And I think we'll probably get there, but let me cut this process short a bit, and let's just go to 1,000 rectangles and see what we've got. 39 even. That's an interesting number. What if we went to, instead of 1,000, 10,000? We add another 0 here. It's still 39.0000. It looks like we're coming very close to a limit. And that means that we're actually getting a very accurate result by now. It may have taken us 10,000 rectangles to do it, but we can manage. Okay. So now this is a tremendously important technique. And let's look at this technique in a little bit more detail and give students some experiences to talk about, to compare one experience with another, to compare different methods of setting up these rectangles. And I actually have some tools that are pre-made to allow us to do this, but I'm going to start out by making a tool of our own, just so that you have a chance to see how it can be done. And what I've got here is a function, a cubic, which is controlled by these 4 parameters. We could modify them if we wanted to. For instance, we could change the value of d, same method as I used before with the plus sign on my keyboard, or the minus sign to bring it back down to 1. And we've also got some parameters here that we're going to make use of. The height just indicates the height of these grid cells that you see. The width is the width that we're going to use for our rectangles. And that width is actually tied to the fact that we're going to start at x equals 1 and finish at x equals 9. So the width of our interval is going to be 8 units. With 8 rectangles, the width will be 1. And this parameter down here is going to allow us to change the number of rectangles we use. So if we go to 16 rectangles, we'll need a width of 1/2. So let me just start by making 8 rectangles for us. And we're going to do 2 things here. First, we're going to look at how to make a rectangle, and we'll turn that into a tool. And secondly, we'll look at how to iterate that so that we end up with an adjustable number of rectangles based on our iteration. So first, the rectangle itself. To create the rectangle, I'm going to use this as a starting point because I'm not saying ahead of time that the rectangle has to be on the x-axis. I will eventually put it there. But I'm not going to say that from the beginning because I want to use an independent point as the beginning part of my construction to make it easy to use this tool later on. So that's going to be my point. I'm going to measure both the x and the y values. There they are. I'll make them slightly larger for you. And let's call this point P, let's say, for the beginning point of our rectangle. So that's the first point. Now, the second point of the base of the rectangle, let's see, if it has to be 1 unit wide, I should take the x value, and to that x value, with Sketchpad's calculator, I will add the width. So now, if I take that new x value and the y value of the original point and plot that point, that will be the base of my rectangle. So now let's figure out where the top of the rectangle should be. And we'll do that by evaluating the function right above point P. To evaluate the function, we'll again use the calculator. We'll click on the function itself to say we want to evaluate that function at the x value of point P. So there's the value of the function. If we plot the point with this x value and this y value, that should be right on the function. And the fourth vertex of our rectangle is going to be x plus the width and the value of the function. So we'll plot that point as well. Select the 4 vertices. Construct the quadrilateral interior. And I'm going to make it look nice, I'm going to select the parents, which are the 4 vertices, and I'm going to construct the 4, not lines, good thing we have undo here, construct the 4 segments. Nope, not that either. Let me get the order correct.
Hey, Scott, why don't you show how to use the polygon tool?
That's a good point, especially for folks who haven't upgraded to Sketchpad 5 yet. I've just chosen the polygon tool. Here we go. However, I chose the wrong polygon tool here, Andres, because I didn't do the segments. Oh well. The polygon tool comes in 3 flavors. The first flavor just does the interior of the polygon. The second flavor does the interior and the sides. And the third does the sides only. Now, I've got a confusing situation here for you. Let me straighten it out. I actually had a polygon, but it came up white for some reason. So the polygon I already had. So all I need to do is add the sides. So I'm using the third flavor of the polygon tool here to do the sides only. And here they go. 1 side, 2, 3, and 4. And there's polygon. Okay. We want one more thing here, which is I want to have the area that's represented by this rectangle. And the area, for the area, I'm actually going to use the area as if it was on the x-axis, which is going to be the width times the value of the function. So calculator one more time. And here we go. The width times the value of the function. And let me rename that as area. Okay. So what I have here is a function, a rectangle that uses the function graph, or the value of the function actually, to construct the rectangle, and a resulting area calculation. And I can use Sketchpad's custom tool facility to use that to create a new tool and call that tool my rectangle tool. And we can actually see, oh, I left something out here. I know what I left out. Hold on, I'm going to cancel that and then explain this script view again in a second. I'm going to cancel this because I don't see the area coming up down here, and I just realized that the area needs the width, and I didn't select the width as part of the tool. Now with that selected also, let's show the script view again. The width is now included. Here we have, let's see, there's the calculation. XP plus width. What did I leave out this time?
Do you need to include the function?
Yes, thank you, Andres. I thought I selected that the first time. Maybe I didn't. Okay, I finally got all my selections right. The rectangle itself, givens include the function and the width of the rectangle, and the output includes the rectangle itself and the area. Nothing like messing up in front of a big audience. Sorry about that, folks. This time we've got it. The area is included. So this is our rectangle tool. And now that I have the tool, and we can look at the script view to see exactly how the tool works, exactly what things we constructed to go into it. That's a very useful thing to do, but we don't want to look at that anymore because we're satisfied with it. And I can actually get rid of the original example from which I made the tool and just start using the tool. Let's go. Rectangle tool. Here we go. First rectangle is going to be based on match point P. I'm looking at the bottom right-hand corner of the screen. Does everyone see down here, match point P? That's the first thing I have to match. Now I have to match the measurement width, and now I have to match the function. And then the point, the width, and the function. And we're getting an area measurement each time. I'm going to show once more the script view to simplify this a bit, because this tool can assume certain objects. I didn't have to indicate what coordinate system I was using, because that's assumed. The width can be assumed also, and the function can be assumed. So if we use the width and the function as assumed objects, Sketchpad will say, well, this thing is named width, that matches, so that'll be the assumed width. This function's named f, that matches, that'll be my assumed function. So now I'll only need to match point P. So let's go ahead and do that. Match point P. And again, and again. So it's a little bit of work to actually create the tool, but once we've got the tool, it's very useful. And we're going to be using a bunch more tools in just a moment. So I can add all these values up, and that gives me a decent result, and use the calculator to add them up and so forth. I'm not going to be completely happy with that when I decide to change the number of rectangles, however, because n is equal to 8 right now. 8 takes us from x equals 1 to x equals 9. If I double the number of rectangles to have the widths, using the plus key on my keyboard again, so I want 16 rectangles, but I've only got 8 here. And that's because I actually made the rectangles with a tool, and I would have to make, I've got space now for 16 rectangles, and I'll have to add 8 more and redo my calculation if I had calculated it already to get up to my 16. Well, this is going to make it pretty hard to go to the limit and to try to find out what the limit is as we get the rectangle smaller and smaller and smaller. So the tools are very useful for illustrative purposes, but they're not going to be so great for moving towards the limit. And I'll take, I'm trying to decide whether to show you iteration right now or whether to look at some of the other tools. I think I'll show you the other piece I'm going to show you. And then we'll come back and do the other tools afterwards. But let me show you the iteration method for doing this with the tool that we've already created. So let me start with a rectangle. Okay, I lost my, when I deleted everything, I lost my point at, I'm just undoing to the very beginning. Here we are, back to the very beginning, but I still have my rectangle tool. I wanted to get that point at x equals 1 back again. Okay. So I'm going to use iteration to make a whole bunch of these that match the correct number that we want. But I'm going to do one more thing that I didn't do earlier, and that is this. With my area, I'm going to say, I'm going to do something that not only iterates the rectangles, but that also iterates the area, so that each time we'll add a new amount onto a beginning area, which I'll start at 0. So I'll need one more calculation to do that. This one right here is going to be my starting area of 0, and I will add to it the area of the new rectangle that I just created. So this is now my cumulative total. So I'm going to rename this last one as cumulative. So now we're ready to iterate. Using Sketchpad's iteration capability, we'll start with our initial point. I think I'm doing this right. I might have to back up in a second, but we'll see. I think I got it right. We'll start with that initial point and with this initial area of 0. I'll also select n minus 1, the number 7, because we already have one rectangle. I need 7 more. Holding the Shift key, transform, iterate to depth, lets me iterate this point to here. There are my rectangles. And notice right now, notice this table that's about to appear, and the cumulative numbers here actually show not the cumulative total, but they show what happens from adding 0 to each of the individual. In other words, they show the individual areas. So this last area right here is 5.82. The one before it is 8.71. And that's because I haven't yet mapped area to this cumulative calculation. Now the cumulative column shows what happens if we iterate the rectangles and we also iterate the calculation. So it starts at 0, then it goes to 0.9, and then remember this is an addition, so then it adds the next area to it, adds 2.19 to it, and then it adds 4.29 and so forth. So with that iteration in place, now we see that the total area is 46.39. Okay. And now we have the ability that we're looking for of changing the number of rectangles and getting a total for our area. So the cumulative total right now is 46.7. That's the sum of the areas of all these rectangles. And we can do what we did before and just hold the plus key down with n selected and watch what happens to the area, 46.71, 46.70. And we may be getting to the point where it makes some sense to have this displayed not in tenths, but perhaps in 10,000s. Let's go to 4 digits. And then we can see more changes take place. Or I can just cut right to the chase and say, well, instead of 142 rectangles, let's do 1,000 and see how much it changes. 46.6894. Remember that. I'm about to press the return key. 46.6730. So it changed by a little bit, not much. 6730. Let's go to 10 times the number of rectangles. 6703. So it only changed by by 2 or 3 thousandths, going to 10,000 rectangles. So we're really pretty close to the limit. Okay. So that's the two constructions that I wanted to show you how to do. And I just want to give you a quick look now at the tools that are already created that come with this presentation sketch that you'll be getting with the resources for this webinar. The other tools that we have available that have been put into, that I've created and put into this, well, I'm not going to show you the left rectangle one because we just did one. The right rectangle uses the value of the function on the right edge in order to construct the rectangle and to calculate the area. So for any given curve, we could say, well, take a look at the left rectangles, take a look at the right rectangles, which seems to do a better job of approximating the area. And part of the reason for looking at all these different ways of constructing rectangles is to familiarize students with the different possibilities. And part of it is just to get them thinking more and more about how that process of creating and adding up rectangles actually accumulates the value of the function. So let me...
So Scott, I'm going to stop you for a second and bring up a couple of questions. So just to clarify, the thing you're talking about right now, you're talking about the custom tools, the right rectangle, left rectangle. These are custom tools that are already pre-built that come with this particular sketch, correct?
That's correct.
But the first thing, the last 10, 15 minutes, you were explaining how to create your own custom tool, your own, I guess, left tool, was it? From scratch, just using Sketchpad. But you did use a couple of givens in this sketch. Maybe you could, for example, the n equals 8, that's just a straight parameter, correct?
That's correct.
That's just a numeric value. But your width value is calculated from n. Can you show how that is done? There was a question about how did the width change when you changed to n.
Yeah, I should have clarified that from the beginning.
That's okay.
When I created this sketch, it seemed it's easiest for this purpose to just change the number, and the width was set up as a calculation. So by double-clicking the width, we get to see the calculation. And the calculation is the difference between x2 and x1, which in this case is 8, divided by n. So that gives us the right width to fit n rectangles in there.
Okay.
It may make more sense, actually, as I think about it. When we think about this in calculus, we usually say, well, we're looking for the limit as the width approaches 0. There are other situations in which we want n to increase without limit when we're looking at limits of different kinds of limits of sequences, and that kind of thing. But in this case, we might want to say, well, let's make our given the width and let n come from that. And we could have done that very easily also. So for instance, I could say, well, let this width be 1 for now, and we'll change it later. So now they're no longer tied together. If I increase or decrease n, it does nothing to width. So I'm going to take this n parameter, and by right-clicking it, edit the parameter, and say, instead of width, I want n to be the, let's see, what do I need here? I need x2 minus x1 divided by the width, right? Isn't that correct? Let's see. If I make the width 1/2, n is 16. Now this will give us a little bit of trouble because there may be widths that we choose that don't give us an integral number of rectangles in here, but the error that's introduced in that way is going to become vanishingly small when we get to the point of doing 300 or 1,000 or 10,000 rectangles. So it's not really going to matter that that the rectangles don't exactly match this, because they'll come very, very close to coming out to 9 at the end.
We have one other question that came up. Shouldn't the area of the rightmost rectangle be 0?
That's not so clear to me, because the value of the function may not be exactly 0 when x equals 9. Let's find out. Let's calculate the value of the function for 9. It's 1/10. So the value of the function is actually 1/10 here. It looks surprisingly close to 0, but it's not quite at 0. I'm just dragging the domain slightly, and if I make this function hairline thin, you can probably see that it crosses the axis very slightly to the right of the tick mark at 9. So in fact, that rightmost rectangle is not 0. Okay.
Cool.
Anything else before I show a couple more tools?
No, we're good to go on. Thanks.
Okay. So the other two tools I want to show right now are a midpoint rectangle. So here's the midpoint rectangle. And some folks may think that this is kind of cool because it means that the gaps are significantly less. In fact, it doesn't give a much better result than the others, because every rectangle has both a missing piece and an overlapping piece. So we still have some errors that result from this. We can get an even better result with the trapezoid. These look like they fit very nicely. And again, we're generating areas here. We can do the same thing with iteration that I did earlier and create a very nice way to get the total set up. So all of these ways are pretty interesting ways of giving kids practice in going through, in reducing the width, getting more and more accurate results, and with the iteration, which I haven't taken the time to do on each of these other rectangles right now, with the iteration getting an approximation that they can see approaches a limit. So that's something we really want kids to do. All right, I'm going to stop for a moment to see if there are any more questions, and then I want to look at the actual definition of a rectangle using Riemann sums and I'm sorry, the actual definition of an integral using Riemann sums, and show you show you how we go from there to approach the fundamental theorem of calculus.
So we got one question about, can you zoom in on the curve to see the area, the last question about the rectangle being 0. How can you zoom in on the curve there?
To zoom in on the curve, here's what we could do. Let me, I assume we want to just zoom in on the place where the function crosses the x-axis, right?
For example.
That's what I understand the question to be.
Yeah. How do you just zoom in?
So all we need to do to zoom in is we can change the scale of either axis. So I can zoom in on the x-axis this way, and if I want to keep the y-axis doing something similar, now I'm going to have to scroll over quite a ways here. Let's see. We're getting close. I'm actually not scrolling, I'm just dragging here. And here we are, pretty close to the 9, and you can see there's 9 and there's 9.5. So the root of this cubic right here is going to be, that would be 9.1. It's going to be somewhere between, it looks to me, between 9.01 and 9.02. And we could zoom in a little bit more if we wanted. I can actually zoom more effectively if I'm at the origin, but I don't want to look at the origin. So let's see. There we go. So now we're showing at 2/10. So that's 9.1, that's 9.05, so we can estimate it pretty carefully. Okay, so that's, all right. Other questions?
No, I think it's good right now. Thanks.
Okay, I see one more question that just came in. The question, how much GSP work do I expect students to actually do, or is this only a demonstration tool? This is, my answer is yes. I do think that it's very valuable for students to do some of these constructions by hand. I think that the process of actually placing rectangles with the tool and then of using iteration to make multiple rectangles, I think those are very useful processes for kids to go through, because that actual physical process of building the thing themselves is something that has meaning to them. It's something that they will remember. It's not something that they're going to, they cram for on a test and then forget the next week. So I think it is very valuable for students to have that experience. That said, we can't do that every time, and we can't give kids direct experience with everything we want to teach them. So were I teaching AP Calculus right now, I would have them doing some work in the lab, actually experiencing themselves, and some of it I'd be using as demonstrations in front of the class. So I would use a mix, and that's what I encourage you to consider doing.
Can I just add that it sort of depends on your resource constraints. I mean, using a projector as a demo tool is great, and for a lot of teachers, that's all they realistically have available to them. So, these things can work great as demonstration tools, but they're also great student activities if you have access to those kind of resources. And I'm also going to push you a little bit, Scott, since it looks like we have about 16 minutes. I want to make sure you have time to get through the rest of your topics.
Okay. Let me run through this one pretty quickly. There are a couple of points I want to make about Riemann sums, which are what we've been looking at are actually Riemann sums. The general Riemann sum I'll talk about in a second, but I want to talk about two very important ones first, which are the lower Riemann sum, which is constructed as a set of rectangles based on the smallest value of the function during the across the width of that rectangle. So we start off with two 3 left rectangles because the lowest value of the function is at the left of those rectangles. But here, the smallest value of the function is at the right, so we get a right rectangle there. And in fact, if we were to move this first green one over, we would see that we don't have either a right or a left rectangle here because the smallest value of the function is somewhere in the middle. So this is a lower Riemann sum. And if we were to look at a midpoint sum in which the midpoint of the rectangle determines the value, the spot at which we evaluate the function, we would see that the midpoint rectangle is consistently higher than the lower rectangle, as only makes sense. And then we can also look on the same sketch at the upper Riemann sum, which takes the highest value in that interval and uses it for the height of the rectangle. So here we have a lower sum that when all four are added up, and this is done by iteration, the same as I showed you a couple of minutes ago, is 11.49. The upper sum is 16.71. And the midpoint sum is in between the two. The definite integral, which, because we know some more advanced techniques, we can determine the definite integral is actually 14.44. So the midpoint sum is pretty close. The important thing here is for students to realize that by increasing the number of rectangles, that the lower sum and the upper sum are getting much closer together. They were quite far apart to begin with, and now they're only a certain number of tenths away from each other. And if we keep going, we see that they're only about 2/10 away right now, and we're only up to 95 rectangles. So if we go to 1,000, let's say, now there's only a 2/100ths difference between the lower sum and the upper sum, and everything has converged on that definite integral on the actual area measurement under the curve itself. So that's an important concept for students to get, and looking at the upper and lower Riemann sums helps prepare them for the definition of what an integral really is. There's one other thing I just want to mention quickly on Riemann sums, and that is that the general definition of an integral does not require the even width intervals that we've been working with. In fact, the general definition of a Riemann rectangle is that it can be of any width at all. In fact, let me put a couple of them here just to make the point. It can be of any width, and we can make an arbitrary choice of where in the rectangle we evaluate the function. These red points indicate where the function's been evaluated, and I can move that point to the right and make it an upper rectangle. I can move it to the left and make it a lower rectangle. This one I can drag around until I find the very highest point and make it an upper Riemann rectangle. The definition of the integral does not depend on the width or on where within that rectangle you evaluate the function. It depends only on the principle of reducing the width of the widest rectangle. And if you sufficiently reduce the width of the widest rectangle, all the other rectangles have to shrink as well. And it's the widest rectangle that controls the definition. So that's an important thing for kids to get, and this Riemann rectangle tool will give you a chance to actually explore that idea. Okay, final thing I want to do here is to accumulate the areas, and we actually did that through a table earlier. But in this case, I want to accumulate it in the form of a graph, because if I do it in the form of a graph, we can actually get values out of that. And this time, I've got the directions here partly to give me a little crutch and partly so that you have them available when you get this sketch and you can follow the directions as well. This point A is going to be our starting point for the area. And remember earlier I made it 0, and if I had put this at 0, we'd have a starting point of 0, but then this would get confused with the rectangles we're going to do. So I'm going to make the starting point of the area a little bit higher just to keep it clear from everything else. Okay, measure the x-coordinate, that's already done. H is going to be the width, so we'll add h to the x value, so x plus h. This is like we just did before. Okay, and we're going to evaluate f at that value of x. So here's f at that value of x. Okay. Put these guys over here. And now we can make our rectangle. And we can also calculate the value of the function times h. So that's going to be the area of this rectangle that we're about to create by plotting x of a and the value of the function. That's one point. X of a plus h and the value of the function is another point. And I'm going to move air, okay.
Did you have those two reversed?
Oh, wait a minute. I didn't do that right, did I?
I think you might have selected the x and y values in the opposite order. No? For the second point?
No. No, what I wanted to do, I don't want this point here. What I want is for my rectangle, this is going to accumulate the area. For the rectangle, I want 2 points on the x-axis. The 2 points I want on the x-axis are at x and at x plus h. I want to plot them on that axis. So those are the points I want. That's my rectangle. Okay. So now I'm set to go. Select the 4 vertices. Construct the rectangle. Put some sides on it. And now what I want to do is take this area and show how the area increases. If this was my starting area right here, how does it increase over the width of this rectangle? So this represents the starting area. So I could take this starting area and add to it the area of this rectangle. So this is the new area at the end of this rectangle if 5.80 was the starting area at the beginning of the rectangle. So that's going to be the point x plus h, and this graph, plot that, connect those points with a segment, and this segment goes up in a way that shows that accumulates the area of the rectangle that it's controlling. Does that make sense? I hope so. Because now we're going to iterate this point to the new point. So I don't think I need anything else. I can iterate. There we go. And I can hold the plus key for this and make lots more rectangles. I don't care about the table because we've got the area shown here. And all I need to do is reduce the width, and we get narrower and narrower rectangles, and we get to see what happens as we increase the number of rectangles, we get to see how the area is affected, how the accumulated area under the curve, or the accumulated value of the function, behaves over a period of time. And I've run out of time to show you what I really wanted to show you on this one, so fortunately I have it prepared. Ready to go. This is an antiderivative activity. Anyone who came to the May webinar has seen this one. What we've done here is we've taken a point A and said, and a function, and said this function's the derivative. Let's see if we can figure out the original function of which this is the derivative. So this is going to be the slope. What we've done here is point A is, we've drawn a segment whose slope is determined by the value of the function at point A. And if we iterate this process, it turns out that we get exactly the same result that we had. Oops. Hold on. Sorry about that. I want 0.5, and I want lots of these guys. And so it turns out that we get exactly the same curve that we had from accumulating area. And I'm sorry I mistimed our work today.
So Scott,
I wanted to be able to show you these right next to each other, and to make the point of how nicely this illustrates the fundamental theorem of calculus, that accumulating the area gives us exactly the same result as we get by finding the antiderivative.
So Scott, I'm just going to remind people that when they get this sketch, those directions of how to do these two activities are included in the sketch, so they'll be able to try them out on their own. And we just have a couple of minutes, so I'd really like you to show the disk and shell models.
Yep, will do. So the disk, and so here we've got the plot of y equals sine of x in the xy plane, and I've got a three-dimensional coordinate system, so I can rotate the xy plane around the z-axis. I can look at it more from looking down from above. So I have various controls that let me look at it in different ways. And if I were to rotate this graph around the x-axis, I would get a wireframe that looks like this. Let me straighten up a little bit, look at it a little more on edge. Let me get the x and y axes spinning around the z-axis. And so you can see the shape that's made by the rotation of the sine curve there. And we've also built within that wireframe a disk that we can drag back and forth to illustrate how we're going to use a disk and calculate the area of the disk, and then the thickness, use the thickness to calculate the volume, and how we could actually calculate the volume of this rotated solid. We have the ability to change the thickness of the disk, so I can make it considerably thicker than it is right now. So now we have a very thick disk, which is not going to give us as accurate a result. We can make the disk very, very thin, and so forth. So that gives a nice way of visualizing what the disk is, that you can move it back and forth, and so forth. Finally, the shell is similar, only this time we're going to take the graph. I've graphed it slightly differently here, but this is y equals 2 times sine of x, and I've actually graphed it in the xz plane. I may change that on a later iteration, but we're going to rotate it around z in the direction that the spin control takes us, and show that wireframe. So here's the wireframe that we get from our rotation. Let's look at that from different angles here, and you can see that the sine curve is what actually controls that rotation. And I've got some controls here that let me look at more or less. For instance, I can go all the way out to the intersection here, or I can stay back here. And I've got a shell that I can use to look at the different shells that we would have to add up to find the volume under this curve. So let's look at this from on top a little bit and see the shell there inside the wireframe, the shell going from the wireframe surface down to the plane of the x and y axes. So that's part of this as well, and I hope that this is an illustration that will help your students understand what disks and shells are all about in the process of accumulating volume rather than area. Sorry, I ran over.
That's okay.
I apologize.
So Scott, one last question. Someone asked earlier, what happens when you change the function? Maybe on one of the earlier pages, what happens if you change the original function you're looking at? I guess you could show that here as well, but it came up in the context of when you're working on the accumulate tool.
Sure. So if I were to add 1 to the function here, there it is. We have much taller shells. If I were to multiply by 4 instead of by 2, I would get really thin, more steeply up and more steeply down. This works for any of the functions that we were working on. So for instance, this Riemann sum, which had the upper and lower sums, I could leave it a cubic and just modify some of the parameters, or I could say I don't want a cubic. I want to use. I'll take a risk. I'll say I want to use sine of x, and if I'm in degrees, it'll look pretty uninteresting. I am in degrees, so 2 degrees, 4 degrees, 6 degrees. That's pretty uninteresting. But in radians, sine of x looks much more interesting. So any of these functions can be changed to anything you want.
Great. And anyone that was participating in today's session, you'll be able to access this sketch that Scott used as part of this presentation. So you'll have plenty of time to experiment with it and to work through some of the activities yourself. Thank you for attending today. Thank you, Scott, for the presentation. I do see one other question that just came in. How was A chosen in the accumulate window?
In the accumulate window.
A being the starting point. I think it's just that A there, yeah.
Yes, this A, I placed it arbitrarily up here so that it wouldn't interfere with my sketch of the rectangles. In fact, A can be placed anywhere. A serves a dual function here because A controls the beginning of the x value controls the beginning of our iteration of our rectangles. But if I use the up and down arrows instead of the left and right arrows, if with A selected I use the up and down arrows, I see that nothing changes except for my constant of integration. So this is actually an opportunity to say, well, it doesn't really matter. This is where we start. We still get the same shape no matter where we start from. So that's a nice way of talking about the constant of integration and how it's an arbitrary value. I see another question. Will the sketches be sent via email? You'll receive by email a link to the URL where you can grab the sketches. And that will happen within the next couple of days. I also see a question, will the sketches work if I only have Sketchpad 4? And the answer to that is that many of these things do work, and many of the activities that I'm going to include for you were designed for Sketchpad 4, so we'll have a Sketchpad 4 version of the package with most of the activities, but you'll at least need to download a trial version of Sketchpad 5 in order to play with the presentation sketch. The presentation sketch is going to be a Sketchpad 5 only sketch.
Got one other question about the three-dimensionality. If that's built into Sketchpad, or do you have to build that operation? I mean, I think the answer to that question is that it's not part of Sketchpad's native environment, but in that particular model that you presented, the 3D model is already built in.
All the 3D work was done using the perspective tools, which is a set of Sketchpad tools developed by Paul Kunkel and that are freely available from Paul's website. So anyone who's interested in building some of those 3D models, if you search on the web for Paul Kunkel, K-U-N-K-E-L, and look for perspective and Sketchpad, you'll turn him up immediately. Okay.
Andre, don't forget to mention Sketchpad Sketch Exchange.
So thank you for joining us. Thank you, Scott. And as Karen mentioned, we have a new free service called Sketchpad Sketch Exchange, which is at keypress.com.
No, it's sketchexchange.keypress.com.
You do this so much better than I, but yes, it is sketchexchange.keypress.com, which I think Scott's about to show you on his screen. It's just a free a way for teachers to share their sketches with each other, and there's conversation, dialogues as well, so you can go there and check that out. I'm just going to say that for those of you who have not worked with Sketchpad 5 yet, if you're still using Sketchpad 4, you really don't know what you're missing, and you really ought to take a look at the the first new version of Sketchpad that we've really put out in a long time. It has some amazing new capabilities and is a much more powerful presentation tool, in particular because of the integrated hot text. And thank you for spending your afternoon or evening with us. Thank you also to Karen and Elizabeth for helping out with answering questions. We will leave this webinar open for a couple more minutes so that we can finish answering questions people have asked. But this is officially the end. And so thanks again. And I hope to see you at our future webinars. We have technology, software-oriented webinars every month on 2 consecutive days. Try to accommodate different time slots and